Okay, we've talked about how we convert to K-maps and how K-maps can at least help us find a optimal solution. What?
Don't care.
Don't cares. Don't cares and K-maps. K-maps. Some circuits, it actually doesn't matter if that midterm, bless you, is a 0 or a 1. So we can actually take advantage of this by putting a don't care as an X, which means that you can grow the prime implicant across it, or not use it in your final estimation. So for example, if we were over here, and you only need these ones, and these X's may not be here, and that might be from certain analysis. You can tell by previous circuits that these values just aren't going to come into it. You do a complex analysis and find that out. Then you can put X's right here, which means that if you're in this one right here, you could grow it to 2, but since you have 2 X's up here, you can grow it up, and you have 4 X's over there, you can grow it even bigger. This is handy because, excuse me, for this big of a box, the cost is far less than if you're going to do them individually. And they actually show that up here, because if you do it with the don't cares, this is just W plus what we got, XZ, which are these 4 guys, and then plus YX, which are these 4 guys. If we treated the don't cares as zeros, we would have to use, what was it? Y naught XZ, which is these 2 for the first term, and then Y naught XY, which is these 2, and then for down here, it'd be W X naught Y naught, which would have a gate input cost of 12 as opposed to 7. So can you at least see how the don't cares help us out? Yeah. One thing to keep in mind, let's just say, for sake of argument, this was an X, and we didn't want to include it in the final estimation, in the final circuit. That's perfectly fine, because an X means it can be 1 or a 0. We don't care.
So we don't have to include it.
You don't have to include it, or you may include it, but it helps you determine what the optimal solution is. All right, so optimization algorithm, find all prime implicates. Hopefully that's somewhat intuitive that a computer can do that. Then find all the essential prime implicants. Again, hopefully that should be pretty easy once you have all the prime implicants. You just go through the list and find which ones, which squares only have 1 prime implicate. This is the hard part. Select a minimum cost of set of non-essential prime implicants to cover all midterms not yet covered, obtaining an optimum solution.
See reading supplement.
Yeah, the reason why it says C reading more is, from my understanding, this is not a tractable problem. Those of you taking algorithms, you'll know exactly what I mean. Those of you not, there is no, just for the time being, there is no practical solution that will always give you an optimum solution. All right?
Good luck.
That's what it means. But we can use heuristics to get a good solution, maybe not a guaranteed optimal one, but a good one. And maybe our good one is optimal, we don't know. All right, now they're going to go through the rules. So prime implicate selection, minimize the overlap among prime, right, as much as possible. Okay, we know that. You okay? So first step, selection rule. Are you going to show the picture, or are we just going to freeze? Oh, it's just going to freeze.
Yay! It's gonna move like 6 sides in a second.
No, there it goes. It's showing. There are the prime implicates. I mean, there are all the prime implicates. And then if you look at, these are all the prime implicates. We're just showing you how it's done. Which ones, which blocks only have 1 prime implicate?
The one in C.
This one and
that one.
that one. So what does that mean?
Those are the 2 essential.
Right, we have to include those 2. So we include those. Now, how do we know which other ones to choose?
Ooh,
Good
you
luck.
could do.
Good luck.
Good luck.
You could just do the goodness, what is it?
Corners. Oh, just do the corners on the.
You can do these 2 corners and these 2 guys.
Yeah.
Yeah.
Right?
Ta-da!
Sure.
That
Okay.
gets them all.
In that case, it is the essential, and then we could find that those two are the optimal. But we'd have to somehow know that that these two guys, this one right here and this guy right here, were not needed to be in the final one. Heuristic here was obvious, pick ones that don't. First off, you could say one heuristic is make sure you pick ones that don't already overlap. The issue is if you pick this one first, then that would not give you the optimal solution afterwards. So
pay attention.
yeah, there are a lot of heuristics here to figure it out. All right, again with don't cares. Let me get my good old handy eraser. All right, we'll make them go highlight them. Is that all of them? All right. So which ones are the essential?
One on the left. And
This guy?
The one in the right corner. That one.
And this one. Notice that I know an X can be one. Or maybe not. Why is this midterms by essential? Oh. Right. This one is not. Sorry. This guy is, and he's just saying that with X, these two are midterms. So our final, my apologies on that one, the essentials right here, and then we have to figure out the selection of the other ones. Probably that one and that guy as well would be a good solution. Unfortunately, choosing the selected ones is not a practical, it's not a easy one. What's that?
We left out one of the X's.
That's fine, because we don't care if it's included or not. Yeah, hints don't care. He can be included or not. We don't care. Yeah.
Not important.
All right. Automated optimizations. Right, you gotta have your midterms as a starting point. Verilog's not, it can generate those. Required determinant of all prime implicants, right? Or require a selection process with potentially very large number of candidate solutions to be found. Because if there's a lot of prime implicants, it's gonna take a long time to select everything.
Right.
Sure.
End up having a suboptimal algorithm that we generally alleviate on the third one, where we don't necessarily select all the correct prime implicants, or the most optimal, prime implicants. Okay. The rest of these slides would actually go through the algorithm espresso. That is the common way of going about it. I don't think that's very important for this class. If you ever get into digital logics, you will probably look at that algorithm a little bit more. But I think you have enough of the understanding of digital circuits for the rest of this course. We are going to still go into talking more about gates and how we create other I don't know how to say this, other architectural structures. But for now, I think this will be good enough for how we optimize circuits, or at least how Verilog optimizes circuits a little. Are there any questions?